Hi, everyone. Welcome to another session of discrete optimization talks. Today, we start with Yongchun Lee from the University of Tennessee, Knoxville. She received her PhD in operations research from Georgia Tech. Her research interests lie at the intersection of optimization, machine learning, and statistics with the goal of advancing machine learning towards greater interpretability, efficiency, fairness, and robustness. Now, Yongchun has received large set of awards, many from student paper and poster competitions. So in particular, she received the first place in the 2019 Mixed Integer Programming Workshop poster competition. Mixed Integer Programming Workshop is happening in Minnesota in June with registration opening, I guess, today or so. Stay tuned for that. And there was a poster competition for you to attend, and even a contributed session this year for all the non-students who would be interested in presenting. She has also won student paper competitions and runner-ups, such as the Informed Computing Society in 2021, and other awards. We're happy to have her lead off today's thoughts.
And thank you for the nice introduction, and thank you for all the organizers to invite me. It's a pleasure to be a speaker at discrete optimization talks. Today, I will share my recent work on strong formulations and the algorithms for regularized A-Optimal Design. First, I'd like to start with the motivation behind the regularized A-Optimal Design problem. It's an application about designing code star survey for movie recommendation systems. In a typical movie recommendation system, users can provide feedback for movies they've watched. For example, by giving a rating number from 1 to 3. And with a lot of historical rating data, we can train some algorithms to predict users' preferences and then suggest movies they are likely to enjoy. That's the foundation of how movie recommendation systems work. But if a new user enters the system, they haven't rated any movies yet, and the algorithm don't have any prior information on these new users. So it's challenging to make recommendations to learn their preferences. And this problem is known as user code star recommendation. To address this problem, a straightforward approach is to directly ask new users to rate a few movies in initial surveys before they enter the system and receive recommendations. This leads to a research question. So which movies should we select? Should we ask new users to rate them? That selection shouldn't be random. A-optimality is a widely used selection criterion in experimental design and has recently been applied to code star recommendation. A-optimality aims to minimize the trace of the inverse of the facial information matrix. Mathematically, it's defined as the trace of the inverse of the sum of AI transpose. And each AI, it represents the existing rating data on the S movie, with I from the indices of selected movies. It's clear A-optimality, it depends on the matrix inverse. So this matrix must be non-singular. However, may not be always true because look at this matrix. It's a sum of AI transpose, and the rank is bounded by the number of selected movies. If the number of selected movies is smaller than the matrix dimension, this matrix is singular. It's low rank, so A-optimality may not be well defined in that case. And this can be a serious concern, especially in movie recommendation system, because new users, they don't want to rate many movies in the beginning due to the cognitive cost. So the number of selected movies usually is smaller than the dimension. To address this issue, researchers have introduced regularized A-optimality, which as a skewed identity matrix, and lambda is a constant, is a positive constant. By adding this skewed identity matrix, the updated matrix is always non-singular, is invertible. And in this formulation, given n data points of dimension D, we introduce binary variable x to represent whether to select the data point AI or not. We let k to denote the number of selected data points. In general, k must be bounded by n, but the value of k can be smaller than the dimension d or larger than the dimension d. We don't have requirement on the relation between k and d. Since we can only choose k data points, that's a cardinality constraint on binary variables x. In this formulation, we see we can reformulate the regularized A-Optimal Design as a integer convex nonlinear programming. The objective function is convex, but we have binary variables, and the objective function is nonlinear. Beyond the CoStar recommendation, this formulation also finds applications in Bayesian experimental design, sensor placement, and active learning, but it's challenging to solve it to global optimality. So most of the existing work has focused on developing approximation algorithms, the randomized sampling algorithms, and greedy algorithms, which provide a feasible solution for the problem routes. And their algorithms are often efficient, can return a high-quality solution in numerical experiments, but their theoretical performance guarantees still leave room for improvement. Because for sampling algorithms, we see the approximation ratios. They only apply to certain ranges of k. It does not apply to any k. As for greedy algorithms, the drawback is the approximation ratio. It relies on the data, relies on the experimental setup, so their approximation ratios can be arbitrarily large in some cases. The work on exact algorithms of ROAD is limited. A recent work by Hendrik et al., they provide an efficient framework of branch-bound algorithm, where they use Frankfurt algorithm to solve the convex relaxation at each node. However, their branch-bound algorithm uses the conventional relaxation bound, and we demonstrated this bound may not be so strong in some cases. To fill in these research gaps, we developed strong formulations, exact and approximation algorithms with performance guarantees for solving ROAD. So before I present our results, is there any questions so far? Okay. Next, I will present several equivalent formulations of ROAD and investigate the optimality gaps of their convex relaxations. First, we prove this problem is NP-hard by reducing independent solid problem to it. And this proves a conjecture from Hendrik et al. They conjecture the problem is NP-hard, and we prove it. This NP-hardness motivates us to develop strong formulations, which makes solving ROAD more practical. Let's start with the conventional convex relaxation of ROAD, which is obtained by relaxing binary variables x to be continuous. And we refer to the relaxation as ROAD R1. We let real well 1 denote its ultimate value. And this 12 based on knowledge, this is the only relaxation that has been used in the literature of ROAD to provide a lower bound. We analyzed the performance of this conventional relaxation by deriving its automatic gaps. It turns out the automatic gap, it depends on the value of k. If k is less than the problem dimension d, we construct that worst case such that the ratio between the ultimate value and the lower bound goes to infinity as lambda goes to 0. And if k is equal to d, the automatic gap is bounded by the minimum between d and n minus d plus 1. If k is greater than d, the automatic gap becomes n minus d plus 1 over k minus d plus 1. So from these automatic gaps, we see the conventional relaxation ROAD R1 can be quite weak if k less than d. But why it performs poorly for k less than d? Like I said previously, if k less than the matrix dimension, this matrix, sum of xi, ai transpose, is low rank, and its rank is exactly k. Suppose sigma 1, sigma 2, until sigma d are eigenvalues of this matrix. Then the last d minus k eigenvalues must be equal to 0, because the rank is k is less than the dimension d. And given these eigenvalues, if we add a skewed identity matrix to this matrix, and compute its inverse. The inverse matrix will have eigenvalues like 1 over lambda plus sigma I from 1 to D. Since we have 0 eigenvalues, the corresponding eigenvalues of the inverse matrix become 1 over lambda, and we have D minus K such eigenvalues. Then it's easy to compute the objective value of ROAD. It's just the trace of the inverse matrix, which includes the term D minus K over lambda. So we can see it goes to infinity if lambda goes to 0. Therefore, the ultimate value of ROAD can be equal to infinity if lambda goes to 0. On the other hand, for the contingency relaxation, ROAD R1, because the variable x can be continuous in the relaxation, so this matrix, sum of xi AI transpose, it can be full rank. All eigenvalues can be positive. In that case, we don't have such a term, and the ultimate value of the relaxation must be bounded, so which leads to infinity automatic gap. By analyzing the limitation of conventional convex relaxation, we are inspired to derive a new function to improve the conventional relaxation. For the case of k less than d, our key observation is this matrix is low rank, and only the first k largest eigenvalues they are used to compute the objective function. We can ignore the other eigenvalues. So that's why we define a new function f if k is less than d, and we only use the first k largest eigenvalues. And if k is greater than or equal to d, and the function f just recovers the original objective function of ROAD. So for a binary vector x with the cardinality constraint, it's easy to demonstrate the function f it exactly represents the objective function of ROAD. The trouble is the new function f is non-convex. So we derive its convex envelope using biconjugate and spectral function theory. Due to time limit, I won't show the details of the derivation of the convex envelope, but we do have an explicit expression of the convex envelope. And by using the convex envelope, we show even if x is binary, the convex envelope is still equivalent to the objective function of ROAD. So by replacing the original objective function with the convex envelope, we can obtain a novel convex integer program of ROAD. Since the objective function is convex, we can derive the closed form gradient inequalities and develop an exact algorithms to solve ROAD to optimality. By relaxing the binary variables of this novel convex integer program to be continuous, we obtain a novel convex relaxation, which we refer to as ROAD R2, and we use rel 2 to denote its ultimate value. We also derive its automatic gaps. Now you see for k less than d, the automatic gap of this new relaxation is bounded by the minimum of d minus 1 over d minus k and n minus k plus 1. And if k is equal to d or k greater than d, it maintains the same automatic gap as the conventional relaxation ROAD R1. In addition, we demonstrate ROAD is equivalent to the A-optimal maximum entropy sampling problem, AMASP. We first established their equivalence using the properties of eigenvalues. AMASP aims to select a k times k principal symmetrics of C to minimize the trace of its inverse. And here C is defined as A transpose A plus lambda times identity matrix of dimension n, and A is a matrix whose columns contain vectors AI. Our previous work derived a convex relaxation of AMASP. Since we established the equivalence between AMASP and ROAD, we can directly apply this relaxation to ROAD problem. And this relaxation relies on a new function phi, and here's the definition of phi. It's a little complicated, but to derive this convex relaxation, we need to compute the Cholesky decomposition of C. And we use H to denote the Cholesky factor. Hi is the S column of H. Since C is a n times n positive definite matrix, so each AI is n-dimensional. And to look at the objective function is based on a matrix sum of xi, hi transpose. So now the objective function is based on n times n metric space. It's more computation expensive because our previous formulations of ROAD, all of them are based on d times d metric space. We use real 3 denote the ultimate value of this new relaxation A mask R. We also derive its automatic gap. For k less than d and k equal to d, it achieves the same automatic gap of as ROAD R2. But if k is greater than d, we construct that worst case such that the ultimate value of A mask R can be negative. Like we know the original problem ROAD, it has non-negative, it has positive ultimate value. So we have a trivial lower bound 0. But this relaxation A mask R, it can be even worse than the trivial lower bound 0. It's because we have a constant d minus k over lambda in the objective function of A mask R, and it becomes negative if k is greater than d. So that's why A mask R can be a really bad relaxation if k is greater than d. Here's a summary of the 3 convex relaxations we've derived for ROAD. We find from their automatic gaps, we find if k is less than d, the conventional relaxation ROAD R1 may perform poorly because it enjoys an arbitrarily large gap. If k is greater than d, A mask R, it may be even worse than the trivial lower bound 0, so it's not reliable relaxation. And in fact, we demonstrate our relaxation ROAD R2. It dominates both ROAD R1 and A mask R. It combines their strengths. Specifically, if k less than d, ROAD R2 dominates ROAD R1. If k is greater than or equal to d, these 2 relaxations are equivalent to each other. And for all values of k, ROAD R2 dominates the relaxation A mask R. Next, I will present 2 greedy algorithms that are used to return a high-quality solution for a ROAD. First, we study the forward greedy algorithm, which starts with an empty set, and then iteratively select a new data point to minimize the objective value until we select key data points. Unlike forward greedy, the backward greedy algorithm starts with a solution of selecting all data points and then remove data points at each iteration to minimize the objective value. The procedure repeats until only key data points are left. This table summarizes the approximation ratios and complexity analysis of the forward greedy algorithm 1 and backward greedy algorithm 2. Interestingly, for the forward greedy algorithm, we prove it has approximation ratio of d minus 1 over d minus k if k is less than d. But the ratio does not hold if k is greater than or equal to d. On the contrary, the backward greedy, it has approximation ratio of n minus d plus 1 over k minus d plus 1 if k is greater than or equal to d. So their approximation ratios are complementary each other. If we combine the forward greedy with backward greedy algorithms, and the output will have an approximation ratio for all k. Finally, I'd like to show the numerical performance of our formulations and algorithms. We use both synthetic data and real data sets. For each data set with parameters and the lambda being fixed, we test different values of k. We use grouping and with lazy constraint and callback functions to implement the cutting plan algorithm to solve the ROAD problem to global optimality. We use gap to evaluate the solution quality. We also report the running time of each method in seconds with a time limit of 1 hour for each experiment. We first compare the 3 convex relaxations and apply the Frank-Wolf algorithm to solve them. The first row, it compares the gaps of the 3 methods of 3 convex relaxations for 3 different data sets. And the second row, it displays their corresponding running times. Look at the figure A. is the data set of n equal to 100, d is 20, lambda is equal to 1, and we consider different values of k. We can see the gap of ROAD R2 in red line is the smallest among the three relaxations. So ROAD R2 outperforms the other two relaxations. In particular, if k is greater than d is 20. So if k greater than 20, we see ROAD R1, ROAD R2, they are equivalent to each other as demonstrated by our theoretical results. However, the gap of A max R in blue, it exceeds 100%. It even reaches 1,750. So it can be really bad lower bound because it returns a negative value in these cases. If we increase the dimension d from 20 to 80, and similar comparison results still hold, because you see if k less than d, now d is 80, the ROAD R1 is a worse relaxation. If k is greater than d, the A max per R is a worse relaxation. It can even exceed 100%. And at the point k is equal to d, our relaxation ROAD R2, it attains the maximum gap. And for the running times, we see the A max per R always takes the longest running time because it is built on the n times n matrix space, while ROAD R1 and ROAD R2, they are based on d times d matrix space. For the largest scale case, n equal to 1,000, we see the A max per R reaches its time limit, 1 hour. So which highlights its scalability limitation. We also compare the approximation algorithms using the same test cases. We compare our forward greedy algorithm 1, backward greedy algorithm 2 with local search and two randomized sampling algorithms. And since there are sampling algorithms, we repeat them 20 times for each case and take the best result. From the first row, we see the gaps of the algorithm 1, algorithm 2, and local search are smaller than those written by the sampling algorithms. So the sampling algorithm returns a worse solution. If we look at the figure closer, we see the local search algorithm and the backward greedy algorithm 2 return a solution slightly better than the forward greedy algorithm 1. The forward greedy algorithm 1 is in purple line, so the gap is slightly larger than the backward greedy algorithm. And for local search algorithm, I like to mention it has a scalability issue because for the largest case, n equal to 1,000, it takes much longer time to implement compared to the greedy algorithms. Now let's compare the exact algorithms to solving the ROAD problem to global optimality. We focus on the cases where k less than d, because for k less than d, our relaxation ROAD R2 strictly improve ROAD R1. We first consider for synthetic data sets, and for each data set, we test three values of k, 5, 6, and 7. In addition, ROAD can be reformulated as a mixed integer second-order Cohn programming, MISOCP. So we can directly leverage Groupie to solve the MISOCP as a benchmark. And for this MISOCP, we also demonstrate its convex relaxation is exactly equal to ROAD R1. So its relaxation is not strong for k less than d because it's equivalent to ROAD R1. We compare the MIP gap and their running times of these three methods. A MIP gap of 0 means Groupie has found it verified an optimal solution. It's clear from the table the cutting plan algorithm using the conventional relaxation, it fails to solve any single case. And MISOCP performs slightly better. It can handle the smallest size case, n equal to 30. In contrast, our cutting plan algorithms, based on the stronger relaxation, it solves most cases within 1 hour. In particular, for the largest scale case, n equal to 100, d is equal to 80, it takes only 1 second to find the optimal solution. Because for these cases, rolled out 2, it provides a really strong, really tight lower bound, and our greedy algorithms return a near optimal solution. So that's why the Groovy can close the gap very quickly. Next, we apply these algorithms to real data size, and now the dimension d is and the size of n is they are larger. But for the larger scale cases, we find MSOCP is no longer available. It runs out of memory, and for the cutting plan with rolled R1, it can solve some cases if lambda is a large value. For example, lambda is equal to 10, it can solve these cases easily. But from our rolled R2, our cutting plan based on rolled R2 still performs best. It can solve almost all the cases to optimality within 1 hour. Finally, let me summarize the main takeaways for my talk today. And a key observation of the problem route is we find whether the number of selected data points k is less than the problem dimension d is really important, because if k less than d, we find the conventional relaxation, it can yield an arbitrarily large gap. If k is greater than d, the relaxation index for R is not reliable because it may return a negative lower bound. So motivated by their limitations, we developed a novel convex integer programming formulation that provides a stronger relaxation. And this relaxation can greatly enhance the performance of exact cutting plan algorithms when k is less than d. In addition, we developed the forward and backward greedy algorithms that are scalable and efficient, and their theoretical performance guarantees are complementary to each other. Okay, that's it for my talk. Thank you very much. I'm happy to take any questions you may have.
Thank you. We have time for maybe one question or so. If anybody has any. Yes, Alan, you can, I think you should be able to unmute yourself.
Yeah. So I actually have two questions, if I may. So the first one is, from the theory of experimental design, I would expect that the observations would be in the corners of the domain. So did you observe that with the solutions that you obtained from this approach?
Oh, you mean from the experimental design, the value of k? Because
so once you select the design, sorry, the design is in the corners for an A-optimal design.
Thanks for the question. Because here we assume we are given the data points. Okay, the data points that are given, and we want to select a subset of experiments. Just like the value of k to be flexible. It can be larger than the dimension, it can be smaller than the dimension of the experiments. But in practice, I agree, the choice of k can be really important to ensure some estimation guarantees. Right.
The second question is, I also have seen that there are approximations to the inverse, like a Taylor series approximation. That avoids the computation of the inverse from scratch, let's say. Have you considered that as an approach for your problem?
No, I didn't notice that. So you mean we don't have to compute the inverse to compute the A-optimality?
Yeah, so there is so through Taylor series you can build an approximation of the inverse of X transpose X.
But that will be an approximation until we focus on the problem and want to solve it exactly from the optimization perspective. But I think using approximation, sometimes it may perform well in practice. So it can be a efficient approach. But here we focus on the exact formulation.
All right, thank you.
Thank you for the questions.
And thank you, Yongchun, for the presentation. If you have more questions for Yongchun, please stick around. There'll be breakout rooms after our next speaker. Let's thank Yongchun one more time.
Thank you.